Hi, we're Team 6, and our ML project is called Detection and Classification of Brain Tumors. We all know that early detection of brain tumors is crucial, whether benign or malignant. Traditional methods like CT scans and MRI scans have played an important role in diagnosis and planning treatment. And now that machine learning offers a valuable tool for analyzing medical image data, ML algorithms can effectively and accurately detect these tumors and do it at a much faster pace, therefore improving the outcome for patients with brain tumors. So why ML? ML algorithms can analyze medical images much faster than traditional methods. They reduce the risk of human error because they reduce the need of manual interpretation by radiologists, and they can be integrated with various imaging techniques like CT scans, PET scans, MRI scans, therefore allowing for analysis of multimodal data. Our dataset classifies images into three classes of tumors: glioma, meningioma, and pituitary tumors. And it also has a fourth class, the no tumor class, where images are classified only when no tumor is detected. For our ML algorithms, for our methods that we implement here, we use two datasets: the brain tumors MRI dataset, which is smaller, and the brain tumors 256 cross 256 dataset, which is much larger.
We use the following unsupervised learning algorithms along with the PCA input for our project: K-means clustering, Gaussian mixture models, and DB-scan.
We have performed principal component analysis on the image data and visualized the top components to see if there are any trends. And we have observed that 895 components contribute to up to 95% variance. And apart from the pituitary tumors, the rest of the classes were intermixed. And this is probably due to the fact that pituitary tumor images have a distinct image style, which usually includes the eyeballs.
So these are the results of our unsupervised learning algorithms. We see that our unsupervised learning algorithms do not perform that well, with a maximum purity score of about 0.46. So the best result of our unsupervised learning algorithm set was GMM with the PCA of the 1000 components. We see that a couple of tumors are classified pretty well. However, on an absolute scale, the algorithm is not able to distinguish well between tumors. So issues with the unsupervised learning algorithms. So one thing, these algorithms don't deal well with high dimensional data due to the curse of dimensionality. Feature representation, we use linear features as we use a PCA input, but features may not always be linear in image data especially. The spatial information is ignored, that is relative placement of pixels, etc. Cluster shape assumptions, GMMs and K-means assume that their clusters are of a certain shape. Density-based limitations. DB-scan may be sensitive to the choice of its hyperparameters, and also the data is randomly distributed, which may explain its ineffectiveness, and of course, lack of data augmentation. Due to such issues, we decided to explore supervised learning algorithms instead.
We use supervised learning approaches to classify the brain tumors dataset. We use techniques such as SVM, CNN, XGBoost, and transfer learning techniques. First, we use the support vector machines. SVMs are very effective on high-dimensional data like images. We perform two pre-processing steps to apply SVM. First, we convert multi-channel images into single-channel grayscale images, and we perform image resizing. We also experiment with differently resized images, starting from 10 cross 10 to 200 cross 200, and evaluate the effect of dimension reduction. As we can see, as the dimension increases, the accuracy of SVM also increases, but saturates at the dimension of 50. We use this for the next set of experiments. For the first result, we use a dataset 256 cross 256 for the brain tumors and use a linear kernel for SVM configuration. And we achieve an overall accuracy of 76% with the following confusion metrics and the class-wise accuracy scores. In order to improve the results, we changed the kernel from linear to radial basis function because radial basis function better encapsulates complex and nonlinear relationships in the data with the same regularization constant. We also use two datasets, the 256 cross 256 along with the MRI dataset, and we increase the accuracy to 86.56% with the following confusion matrix and the classification report. We also evaluate gradient boosting techniques like XGBoost, which is known for strong performance and regularization during the training phase. We resize the images to a dimension of 50 cross 50 and perform experiments. For the first result, we just use a single dataset, the 256 cross 256 one, and achieve an overall accuracy of 83% with the default XGBoost hyperparameters. We improve upon the XGBoost prediction by extending the dataset to both 256 cross 256 and the MRI dataset. We now achieve an overall accuracy of 92.98% with the following confusion matrix and the classification report.
We use CNN as another supervised learning method to classify brain tumor images into four classes. We started with normalizing the pixel data by dividing all the values by 255. The input to our model is the scaled input image of size 256 cross 256 pixels with 3 RGB channels. Our CNN model consists of 4 convolutional layers with increasing filter sizes from 32 to 256 and max pooling layers to progressively reduce the spatial dimensions. In the end, the flattened output is connected to a dense layer with 4 units and softmax activation function to output the probability values of the 4 classes useful for multi-class classification. The model is compiled using Adam optimizer, which is used for optimizing the weights of the network, categorical cross entropy as a loss function, and accuracy as the metric. For this setup, we got the following confusion matrix and the precision recall and F1 score for each of the class. Our accuracy metric, which we use for evaluating the model, comes to around 88.4%. So can we do better? To improve the accuracy, we performed the following experiments. First of all, we used a much larger dataset available. So the new dataset consisted of the previous dataset plus additional images of size 512 cross 512 pixels. The second experiment which we did was we performed the image augmentation. And surprisingly, the results improved. So after performing these experiments, we improved our overall accuracy from 88.41% to around 93%. This is the confusion matrix and the precision recall and F1 score for each of the class.
After CNNs, we implemented transfer learning, where we opted for 2 popular CNN architectures, VGG16 and Inception v3. We fine-tuned these models by adding a few dense layers towards the end of the network. We loaded the pre-trained weights and excluded their fully connected layers. Pre-processing techniques like normalization and resizing was done for uniformity in input dimensions, and the Adam optimizer and the sparse categorical cross entropy loss function were used in both the model implementations. Coming to our results, VGG16 showed a very high training accuracy of 99.91%, while its validation accuracy was only 50%. In InceptionNet, the training accuracy was 99.25%, but the validation accuracy was up at 70.8%. The approx time per epoch was 10 seconds for VGG16, but it was only 4 seconds for InceptionNet. We also implemented transfer learning with image augmentation to help improve our results. Pre-processing methods like random flip, random zoom, and random rotation were used. And again, the same Adam optimizer, sparse categorical cross entropy, normalization, and resizing was done. With augmentation, our results changed. The VGG16 training accuracy went down to 97.17%, but its validation accuracy increased to 67.95%. InceptionNet training accuracy went up to 99.79%, and its validation accuracy also went up to 76.64%. The approx time per epoch stayed the same. Summarizing transfer learning results, InceptionNet v3 proved to work much better than VGG16, both with and without image augmentation when you consider validation accuracy. We also tried to extend transfer learning and image augmentation to the larger data set, but that made the models run very long and did not provide any better results, which is why we excluded it. To summarize our project of detecting and classifying brain tumors, we implemented both supervised and unsupervised methods. The unsupervised learning methods did not show very ideal results, but our supervised learning methods achieved great results.